we'll directly go to the topics. I mean, we'll go to the class straight away. So we'll be starting with one of the starting topics from digital electronics, and it also comes in your syllabus in computer architecture. So it is a part of both these subjects. Okay, so we'll be starting with number systems. So we'll go to the basics of number systems straight away. So we're going to deal with number systems. So first of all, let me ask you, sir, if any of you are familiar, you can answer. What is the basic number system we all deal with in the day-to-day? We all are using in our day-to-day life. So if anybody knows the name of that particular number system, it is a decimal number. Very good. I mean, it is a decimal number system, right? So basically, decimal number system is the one we are. So like I said, in day-to-day life, the number system we are mostly dealing with is something known as decimal number system, right? Now, this is fine with our human everyday life, but when we go to this digital electronics, or when you deal with the machines or computer systems, you might be knowing that this number system might not work. I mean, this might not be the obvious choice for machine dealing with the machines. And what do you think will be the? I mean, you might have heard of this one. What do you think is the number system popularly used for interacting with the machines or at the machine level? Which is the number system? If anybody knows that, it's a binary number system. So when you are actually dealing with the machines, we actually go to the binary system, the logic 1 and logic 0 system, right? So already you know these two number systems already. One is decimal and the other one is binary number system, right? Okay. Now, what is common to all these number systems is that now there are many other number systems like decimal. This is binary. These two you will be already familiar with these number systems. And besides these, there are many other number systems like octal number system, hexadecimal number system, right? Now, what is the characteristics of each of these number system, or what is the defining characteristic of each of these number system? Now, the first thing you need to understand in a number system is that, so let's start formally. In a number system, the first thing you need to understand about any number system, whether it is decimal number system or binary number system or an octal number system or a hexadecimal number system, base 7 number system, what you need to first understand what is meant by the base of the number system. Base of the number system. And this is a very important definition. You need to know about this number system, or which is also known as a radix of the number system. Radix of the number system, right? And usually sometimes it is denoted by this letter, usually denoted by R. And what is meant by the base of the number system? So most of you must be knowing that the base of decimal number system is actually, so let me write it. I'll tell you what base is. I haven't defined it. The base of this number system is, from your previous knowledge, you will be knowing that the base of this number system is 2. So what exactly is represented by the base of the number system? So base is nothing but, if anybody knows, this is the definition of base. That is, it is the number of symbols. It is the number of symbols used in that particular number system. It is the overall different number of symbols used in that number system. To represent different quantities. That is, to represent different quantities. And what is the meaning of this one? See, let us take different quantities, right? Let us take a decimal number system. And I already told you that base is 10. And what is the meaning of this base? Base is 10. That is, if you look at the decimal number system, and I already told you it is base 10 number system, so it should have 10 symbols. And what do you think the 10 symbols are? Basic primitive symbols. So the symbols are actually 0. See, if you look at the decimal number system you are familiar with, which are the symbols you are using? The primitive symbols you are using to represent all possible numbers. See, it is a combination of these symbols. What are these symbols? It is 0, 1, 2, 3, etc. up to what? Etc. up to 9. So every other number, that is, these are the primitive symbols we have in decimal number system, base 10 number system, and every other quantity or every other number is represented as a combination of these particular primitive symbols. For example, 10 is the quantity 10 is represented by what? That is, after 9, 10 has to come. 10 is represented by a combination of 1 and 0, and that is represented according to a positional weighting system or weighted position system. I'll tell you what it is actually. Usually 10 is represented by like this one. There has a, I mean, this quantity has a meaning, right? And 321. I mean, these all use these primitive symbols. These symbols 3, 2, 1. It's a combination of these primitive symbols. So if you take any number represented in decimal system, it will be containing only these digits or these symbols. So whatever is the total number of symbols available for representing the numbers in that particular number system, that is known as the base of the number system, right? So in decimal number system, you have got 10 symbols, right? And also one more, and what about binary? If it is a binary number system, and what is the base or base? I'll use the, for base I will be using the letter R. R stands for radix, okay? And for binary, your radix is equal to, what do you think the radix is? What is the base? The base is equal to what? The base is equal to 2. And what is the symbols available for this one? What are the symbols available in the binary number system? The symbols available in the binary system are only two symbols, 0 and 1. And every other number is represented by what? Every other number in binary is represented using the combination of ones and zeros. You have only these two primitive symbols, and every other number is represented by this combination of, for example, if you want to represent 2, see, 0 is this 0 and 1 is 1. And if you want to represent 2 in binary, you actually write it as what? You actually write it as 1, 0. And if you want to represent 3, you actually write it as 1, 1. And how do you write this? This is according to a rule, weighted position system we are following. I'll discuss what it is actually. And every number system follows this weighted position systems. Okay. So if it is binary, you have got two symbols, and the common, and you can have any base system. You can have a base. Suppose I say that you have a base 4 system, base 4 or radix 4 system. And what do you think the symbols will be? The symbols will be 0, 1. The symbols available will be 0, 1, 2, 3, right? And if you want the number after 3, and it will be represented by what? It will be represented by 1, 0, right? That is 1, 0 in base 4 system actually represents which number? This actually represents 4. And if you want to represent 5, it will be 1, 1 in base 4, right? So like that. So, and base 4 system, and then then there are you can have base 6 system, base 5 system, but widely popular. I mean, we will not be discussing too much about the other base 5, base random bases. We will not be discussing too much. The most famous ones are octal number system, and octal, as the word suggests, what do you think the base will be? Anybody? What will be the base? It will be base 8 system, right? Base 8 system. And what will be the symbols available in this one? 0, 1, 2, etc. up to what? Up to 7, right? This will be the symbols available in octal number system. And another very popular one is hexadecimal number system. Hexadecimal number system. And what do you think the base is? If anybody knows what is the base of hexadecimal number system? Well, it is 16 base system. It is a 16 base number system, hexadecimal. And in this one, you have to be careful here. See this one. What will be the symbols used in hexadecimal? So there should be how many symbols available in this particular number system, hexadecimal number system, do you think? The base is 16. There has to be 16 distinct symbols at your disposal for representing every number, right? So what do you think are those 16 symbols? Obviously, the first 10 symbols are 0, 1, 2, etc. up to what? Up to 9. Now after 9, which is the symbol you have? Can I use 10 as a symbol? Can I use 10 as a distinct symbol? I cannot use 10 as a distinct symbol. Why? 10 is actually a combination of 1 and 0, which we are actually using in decimal number system. I mean, 10 is a combination of 1 and 0 because decimal does not have any, I mean, it can use only these two symbols. So after 9, it is forced to go to what? A combination of 1 and 0, right? Yeah. It has to go to a combination because it's a combination of 1 and 0. So it doesn't contra. So for 10, you should have a distinct symbol because you need 16 total symbols, right? So what you actually do is that for any number system which has a base greater than 10, for any number system which has base greater than 10, what you do is that after 9, that is after 9, the next symbol, the symbol you are giving for 10 will be A. So please understand, A will correspond to which value? A will correspond to the value 10 in your normal decimal system, right? So when you say this A, the inherent value of A is what? The inherent value of A in your mind has to be, it represents the value 10, actually, right? So A is a symbol. A is a symbol which we are using for representing numbers in hexadecimal number system. Similarly, the next symbol is going to be B, and B will correspond to what? B will correspond to the value. B will correspond to the value 11, and C will correspond to the value what? 12, right? And D will correspond to the value 13, and E will be corresponding to the value 14. And finally, F will be corresponding to the value. There will be one more symbol, F. This will be corresponding to which value? 50. So there is symbols from 0 to 50, but this 10, 11, 12, 13, 14, 15 are represented using these distinct symbols. We are giving alphabets for that. A, B, C, D, E, F. So whenever you see this A, you should have the value 10 in your mind. Whenever you see this symbol C in hexadecimal, you should have the value 12 in your mind. So C has an inherent value, or the value in your decimal for C is actually 12, right? So these are the symbols you will be using for what? Symbols you will be utilizing for uh, representing different numbers in hexadecimal number system. Okay, so this is basically the base of the number system and different number systems, and what are the symbols used in each of the popular number systems. Now let us come to the representation of numbers and what is meant by weighted position system. Weighted position system for representing numbers. For representing numbers. Okay. And what is this actually? Now, you might be so used to your decimal number system that you might have forgotten how we get to the value of each number. So just for example, I'll tell you this particular number. So let's consider the decimal 123. And what is the actual meaning of one? See, if I represent 123 base, so this is the representation for 123. It is in base 10, right? So that is a represent. This is the notation we usually use, right? So we suffix it with the base. And what do you actually, if you want to get the value of this number, if you want to get the actual value of this number in your normal, I mean, this is already in decimal, so you know it is. Now, how do you get this particular, see, when you say 123, how are you getting this 123? Or what is the meaning of this one? So what you actually do is that you give a weight to this each of this position. So you usually say that this is a units place. When I say it's a units place, what I'm actually saying is that I'm assigning a weight to this position, and that weight is equal to what? 10 raised to 0. The base is 10. If your base is 10, right, I am assigning a positional weight. I am assigning a positional weight to this particular place as what? This is taken as a zeros place. I mean units place, but we will assign it as what? 10 raised to 0. And what is the weight associated with this position? The tens place. We call it as tens place. Why? Because we call it as units place. Why? 10 raised to 0 is 1. So we call it as unit place. And what is the second position? Second position has a weight 10 raised to 1. And what about the third position? The third position has got a weight 100. I mean, it is 10 square. Basically, it is a square of the base. So similarly, and how do you calculate this? Basically, how do you calculate this particular value? You take each number, you take each symbol, or you take each digit. So one, this one is standing at which weight, uh, standing in which weighted position? It is standing in 10 square. So what you do is that this one will be multiplied by what? The weight of that particular position, right? Plus, and this two is sitting in which position? The 2 is sitting in the position of 10 raised to 1. So this 2 will be multiplied by what? 2 will be multiplied by 10 raised to 1. And 3 is sitting in the units place. That means the weight of that particular position is 10 raised to 0. So you will have 3 into 10 raised to 0. And in fact, this is actually the meaning of 123. And you can add, this is nothing but 100 plus 20 plus 3. And that is actually your number 123, right? Right. I mean, this is for base 10 number system. Suppose I give you another number system. Say I tell you what is this particular 322, right? Suppose this is given in base 5 number system, right? Now, what do you think its actual value will be, or what will be this value in base 10 number system, the number system you are dealing with? This is a number system you are not familiar with, but I am telling you that I have a number which is represented as 322 in base 5. I am giving you the base 5 also. So in a base 5 number system, what do you think the weight of the positions will be? What will be the weight of this particular position? What do you think the weight of the position will be? If the base is 5, if the base was 10, it was 10 raised to 0. If the base is 10, it is 10 raised to 1. Now what happens if the base is 5? If the base is 5, what will be the weight of this particular position? It will be 5 raised to 0. Very good. And what about the next one? It will be 5 raised to 1. And what about the last one? It will be 5 square. Right? So this will be the weights of the position. And how do you derive the value of this particular number in the decimal? So exactly in the same manner. See, in this particular case, you don't have to do anything because it is already in decimal. But in this case, you have to actually do that conversion and get it into the decimal value. And how do you get that? You take this symbol. What is the first symbol? 3, or first digit is 3. And what is its positional weight? 3 is standing in which position? 3 is standing with the weight of what? 3 is standing with the positional weight of 5 square. So multiply 3 by what? Multiply 3 by 5 square plus, and what is the next digit? 2, and multiply 2 by its positional weight. And what is its positional weight? It's 3 into 3 into 5 square, or 3 into 5 raised to 3. It is 3 into 5 square. So you're right, actually. Deepak, you're right. It is 3 into 5 square, that is 75. But you have just typed it mistakenly. It is perfectly right. It is 75. But what about this one? 2. Yeah, answer is 87. That's correct. I mean, that's correct. Now, just for the understanding of others, I'll just explain this. So many of you are answering the questions. That's very good, actually. But if others are not getting it, please listen to this one. 2 is having a positional weight of what? 2 is having a positional weight of 5 raised to 1. So you multiply 2 with what? You multiply this 2 with its positional weight. And what is its positional weight? 5 raised to 1. And what about this 2? What is the positional weight of this particular 2? The positional weight of that particular 2 is 5 raised to 0. So what you do is that you multiply with 2 into 5 raised to 0. And can you calculate this for me? Let us calculate this. What is 3 into 5 square? 3 into 5 square is 75 plus. And what is 2 into 5? 2 into 5 is 10. And what is 2 into 5 raised to 0? I mean, 5 raised to 0 is 1. 5 raised to 0 is 1. And what is 2 into 5 raised to 0? It is 2. And what is this result? It is equal to 87. So this is the value in your actual decimal number system. So whenever you want to convert a number given in a particular base, any base number system, to decimal number system, what you can actually do is you can actually carry out this particular procedure, right? what you do is that take every digit, multiply by its positional weight, and you get the value in the decimal, right? Or in general, what you can do is that, suppose I am given enough, and one more thing here, let me just tell you this one also. Suppose I have a number 123. See, you might have seen this kind of a fractional point, right? You might have seen in decimal, but in other number systems also you will have some fractional point here. Suppose you have something like 123.4, say 43, and in base 5 number system, right? So in base 5 number system, in this particular, whenever a fractional point comes into the picture, what will be the positional weight you are assigning to this one? Always understand the digit just to the left of this particular fractional point, it is always assigned the value, raised to 0, base raised to 0, and 2 is assigned the value 5 raised to 1, 1 is assigned the value 5 square. So this is all like the same thing. And what happens to the digits to the right of the decimal point, fractional point? What do you think will be the positional weight of 4? What do you think will be the positional weight of this particular digit 4? Somebody has already answered that. It is 5 raised to minus. See, this is 0, so this has to see in the left direction it is increasing. So when you go to the left, it is increasing from 0 to 1, 1 to 2. So when you move towards the right, it has to decrease actually. So the positional weight of this one will be 5 raised to minus 1. Positional weight of 3 will be what? Positional weight of 3 will be 5 raised to minus 2, like that. And if you want the number in, if you want to convert this particular number into decimal, what you are actually going to do? Take this number, multiply by the take every digit in this number, multiply by the positional weight. So it will be 1 into 5 square plus 2 into 5 raised to 1 plus 3 into 5 raised to 0, right? Plus 4 into 5 raised to minus 1 plus 3 into 5 raised to minus 2. So I'm not calculating this number. So you can actually do this. I mean, for what is 4 by 5, what is 3 by 25, you can do that. I'm just showing you how to convert a number from any base number system to decimal number system, and be familiar with the positional weight system. Now, in general, suppose you have a base R system. In general, if you have a base R, for a base R system, for a base, some random base R system. Suppose I give you a number something like this, say some x3, x2, x1, and these are digits. These are symbols present in this base R system, right? Some point, say some something y1, right? Y2, y3, etc. Right? So suppose this is the number given in base R system. What do you think the decimal value of this number? How do you convert this one to decimal? So what are the positional weight? So what you need to understand, the positional weight of this one will be R raised to 0. This will be R raised to 1. This will be R square. This will be R cube, right? And this one will be R raised to minus 1. This will be R raised to minus 2. This will be R raised to minus 3, right? So it goes like that. And you just start to multiply whatever this digit with its positional weight, right? So basically it will be x3 into R raised to 3 plus x2 into R square plus x1 into R plus x0 into R raised to 0 is 1 plus y1 into, I mean, you don't have to worry about its calculation. I'm just showing this to make you understand that this is how the positional weighting system works, right? Right, so this is y2 into R raised to minus 2 plus y3 into R raised to minus 3. So this will be the decimal value you are expecting, right? So this is how we convert any base number system to a decimal number system. So whenever they ask you to convert a particular base 5 number system to a decimal, now you know how to do that, right? So if they ask you to convert, so let me give you a question, right? See, let me ask you this particular question. Uh, say, um, yeah, we don't want the exact answer. Let me ask you this. Say CAFE, right? Base 16. How will you see this is a hexadecimal number? Please understand these are symbols in hexadecimal. How do you convert this one into I mean your base 10 or a decimal system? This is hexadecimal. So I have given you a number represented in hexadecimal system. And how do you convert this one into decimal? Can somebody tell me what should I multiply each with? Right? Each of these are symbols. Please understand. C is a symbol, A is a symbol, F is a symbol, E is a symbol. Right? And each of them has some values. I already told you what those values are. Right? And first of all, what is the position weight of this one? 16 raised to 0. What is the position weight of this one? 16 raised to 1. What is the position weight of A? It is 16 raised to 16 square. And what is the position weight of C? It is 16 cube, right? So if you want to calculate the decimal value, what you have to do is that it is C multiplied by, basically C multiplied by 16 cube. But you need to understand C, what is the value of C? You need to actually do it in the decimal operation. C represents which value, which decimal value? C is a symbol. C is a symbol used in hexadecimal system, but it has got an inherent value in decimal. What is its inherent value? C represents 12. So it is 12 into 16 cube plus, and what is the inherent value of 10? So it is A into 16 square. But what is the value represented by A? What is the value represented by A? It is 10. 10 into 16 square. And what is the value represented by F? F is a symbol in hexadecimal, but what is the value represented? It is 15. And what is the positional weight of F? It is 16 raised to 1. So 15 into 16 raised to 1 plus. And finally, you have got E, and E stands for which one? E stands for which value? 14. 14 into 16 raised to 0, right? So this is whatever this value, I am not calculating it. It will be a big value. I'm not calculating that one. You can actually work it out. But whatever the value you are getting, this will be the corresponding decimal value, right? This is how you convert from hexadecimal to hexadecimal to decimal system, right? So if you want to convert any base number system to your decimal number system, you have to follow the positional weight. Positional weight, multiply each symbol with its positional weight, and you get the value in the decimal. So that is a conversion from any base number system to decimal number system, right? I hope this is clear, right? So is it clear, everyone? Or you can just give a yes in your chat box if it is clear, so then we can move forward. So if anybody has some doubt, you can actually ask the doubt, and or you can put it in the chat box. Okay, so I think this is clear, fairly straightforward for everyone. So let's move on to the next point. So now we have seen the conversion from any base number system to decimal number system. How to do the reverse operation? That is, suppose we want to convert a number in which is given in decimal. Suppose we want to represent that number in some other base number. Suppose I want to represent a number which is given in decimal, and I want to represent in, say, base 8 system, in an octal system. How do you do that? Or suppose I am given a number in decimal system and I want to represent it in binary. So how do you go from decimal to binary, or decimal to octal, or decimal to hexadecimal? How do we do that? Right? So the next thing is conversion from decimal to any other base. So how do we do this one? Right. So let's take an example. Let's take an example and make it clear, right? So suppose we have this particular number. Let me give you a number, something like say 53, right? And this is given in base 10, and I want to convert it into a number. I want to convert it into its say base 2 binary representation, or some, I mean, it can be base. Let us take another base 5 representation. Suppose maybe let's take a binary representation. Suppose I want to convert it into base 2 representation. So the procedure you have to follow is that, please understand that, please first look at this particular number and check whether there is any fractional point or some fractional part. If there is no fractional part, please understand this entire thing is called as an integer part. That is, suppose you have say 53.26. This particular part is known as an integer part, and this particular portion is known as a fractional part, right? First, you need to verify, is there an integer part and a fractional part in the given number. Now, if there is no fractional part, don't worry about it. When it comes to fractional part, I'll tell you what to do. Now, if it is only integer part, what you can do is that, see this one. What you do is that you repeatedly divide it by this particular base. Whatever base you need to convert it into, right? So it is given in base 10 system, and you want to convert it into which base? You want to convert it into which base number system? You are given a number in decimal, and you want to convert it into which base number system? What is the base of the number system you want the number to be converted? It is 2. So you pick that particular base. You pick the base to which you have to convert the number 2, right? And then you divide by that particular base. So if you want to convert it into base 2 system, then divide it by 2. If you want to convert it into base, maybe base 5 number system, divide it by 5, right? If you want to convert it into base 8 number system, divide it by 8. So in that manner, right? So if it is 2, what you do is that you divide it by 2, and let us do this division, right? So let me tell you, we are not focused on the result you are getting here. We are more focused on the reminders you are getting here, right? Let's see this step by step. See this one. So let us divide this. What is 2 in 53? I mean, 2 goes in 5 how many times? 2 times. Then there is a remainder of 1, and this is 13. 13, 2 goes in 13 how many times? 6 times. And is there a remainder? Is there a remainder in this one? Division? Or, I mean, 2 times 26 is 52. And out of 53, is there a remainder left? Yes. And what is the remainder? Please write it here. The remainder left is 1. Right? Then you repeat this division. 2. Now what is this one? This is 13. And is there any remainder here? I mean, 2 into 26 divided by 2 is 13. And 13 into 2 is perfectly 26. 13 into 2 is 26. There is no remainder in that particular division. So the remainder is 0. Now carry out this division again. So you get 6 with a remainder of what? With a remainder of 1. Divided by 2 again. You get 3 with a remainder of what? 0. And you divide it by 2 again. You get 1 with a remainder of what? 1. And now you divide it by 2. You get 0 with a remainder of what? Sorry, you get you get 0 with a remainder of 1. Now once it is 0, you don't have to carry out the division anymore. So until it is 0, you have to carry out the division, right? Once this becomes 0, you can stop the process there, right? Now you have actually collected the reminders here. Now our idea is to get the representation of the number in the binary system. What you have to do is that, please listen here. You have collected the reminders. You just read it in this direction. You read it from bottom to top. I mean, you write these reminders from bottom to top. That will be your binary representation, or that will be your base 2 representation. So how do I write that? 1 1 0. So this will be my most significant bit. right? So this will be the largest bit. I mean, this will be the leftmost bit. That is the most significant bit. 1, then next one is 1, then it is 0, then it is 1, then it is 0, then it is 1. So this will be your, this should be your, this should be your 53. Right, so is it not 63? You can verify. See, what is this one? This one is 32. I mean, positional weight. This one is 16, right? And this one is actually 4, and this one is 1. So basically, when you add all of these, you are going to get what? I mean, it is basically 53, right? 32 plus 16 is 48. 48 plus 5 is 53. So that is what your conversion is, right? Suppose you want to convert the same number. Suppose you want to convert 53 base 10 into a number base 8. Suppose you want to convert from decimal to octal. So how will you do this? So what is the procedure? Exactly the same procedure. You need to do the repeated division. So 53 has to be divided with which number do you think? Here. If you want to convert this one into base 8 system, 53 has to be divided with which number? What do you think the number should be? It has to be divided with 8, right? So when you divide it with 8, now tell me, 8 in 53, how much time? What is the number of times it goes in 53? It is 6 times. And what is the remainder here? What is the remainder? It is 5, right? And again you go by 8. So this will be 0 and this will be 6. I mean, the remainder will be 6. And you go from bottom to top. So your number will be 65 base 8. So this will be the octal representation of this particular number system, right? What about 53 base 10 in hexadecimal? How do you do that? Suppose I ask you what is, sometimes in hexadecimal, sometimes they will represent it as some H here sometimes. So just remember that's a notation. Okay. So 16, and so what is this one? So 53 has to be divided with what? 53 has to be divided with 16, right? Now tell me this one. 3 times 16 is 48. So 30. Yeah, very good. I mean, you're giving the answers very quickly. I'm very pleased with that. I mean, some of you might be experienced in that, and there might be students who might not be knowing it. And if anybody is feeling difficulty, so please tell me, right? So this one, what is the, you have to track the remainder, not the result, right? So what is the remainder here? Remainder is 5, right? Then this one 16, this will be 0, and the remainder is 3, and you go in from bottom to top, it will be 35. I'm 35. So basically this will be the 35 base 16. So this will be the conversion of 53 from 53 in decimal to hexadecimal, right? So this is how we do the conversion of the integer part. Suppose we have a fractional part also. How do we do that? Say, let me give you one question to convert a fractional part also, right? Suppose I give you this particular number. Say, convert 37. Let me give you some. Okay, 37 point. Say, if remainder is 10, then yeah, correct. I mean, see, when you divide, that's correct. If remainder is 10, then you have to represent it with what? So see, there is one student asking that is, you have some number, right? Say, let me say 96. Okay, say 108, right? Say, suppose you want to say I have to, that's a valid point. So one student has asked this question. Suppose I want to convert 108 in 10 to hexadecimal, right? 16. So how do you convert this one into hexadecimal? See, please understand, it is 108 divided by 16, right? Now tell me, can you tell me which is the nearest multiple of 108? What is the number? I mean, I think 6 times 16 is 96. right? What is the remainder here? What is the remainder? I think 6 times 16 is the nearest multiple. So it is 96. And the remainder is what? Remainder is, I think, is it 14 or 12? It is 12. Now, should I write as 12 here or the corresponding symbol in the hexadecimal? Yeah. What is the corresponding symbol for 12 in hexadecimal? I mean, the remainder is 12. We know that. The remainder is 12. But what is the corresponding symbol for 12 in hexadecimal? It is C. So you have to actually write the remainder as C, right? Then you divide it by 16, you get 0. This one is 6, and now you write it in the from bottom to up, and you get what? This will be what? This will be 6C, right? So that is how you, if the remainder is greater than 10 or greater than 10, then you have to add the corresponding symbols A, B, C, D, etc. Right? So yeah, remember that one. And let us look at when there is an integer part and fractional part, what will you do? Say, suppose I give you a number 37 point, and I'm particularly selecting this number very selectively. I'm choosing this number very selectively, 3125. I mean, to make the calculations easier. Right? So this is so suppose this is in decimal, and convert this one into, so this is aside. One second, this is aside, this calculation is aside. Okay, convert this one into to say binary, right? And so this is our question. Now what you have to do is that take integer part and fractional part separately, because for each of them the procedure is different. For integer part you have a different procedure, for fractional part you have a different procedure. So first let us deal with the integer part. So let us take 37 first, and let us convert that into binary first. 37, right? And what is the conversion to binary? 37 divided by what? I mean the same procedure. I mean, if it is an integer part, there is no worries. Divided by 2. So this will be what? This will be 18 with a remainder of 1. 18 with a remainder of 1. Sorry. This will be 2, 9 with a remainder of, what is the remainder here? 0. Yeah, got it. I mean, 2. Many students are getting the answers easily. Very good. 4, 1. So this will be 2, 2. This is 0. This will be 2, 1, 0. This will be 0. Sorry, this will be 2, 0. This will be 1. And you go from bottom to top, right? So 37 has a binary 1, sorry, not this one, 1, 0, 0, 1, 0, 1. So this is the deal with the integer part. Integer part is converted into binary. What happens with the fractional part? Now, if it is a fractional part, conversion of the fractional part. Conversion of the, so let me write it in the next slide. Conversion of the fractional part. Conversion of the fractional part. So first thing is, what is the fraction you have here? The fraction you have here is 0.310. 3125. And whenever, please understand here, please listen here, whenever you want to convert a fractional part into, whenever you want to convert the fractional part into base 2 or whatever base it is, what you have to do is not dividing. If you want to convert fractional part, yeah, a remainder from top, not the remainder, it is not the remainder, you are not going to divide it here. Instead of dividing, for integer part you will be dividing, for fractional part you will be multiplying it with 2. You will be multiplying it with the base. Now, when you multiply it with the base, can you tell me what is the answer to this one? Now, it might be difficult for you, but let me give you the answer. The answer to this one is 0.625. 0.625. Now, in this answer, in this particular answer, you pick this 0 here. You pick this integer part and you keep it here, 0. So you need to keep track of this integer part in each multiplication. So please understand, whenever you want to convert the fractional part into the corresponding base number system, take the fractional part and multiply it with the base to which you have to convert the number to, right? If you want to convert the number to a base 2 system, multiply the fractional part with 2 and do this in a repeated fashion. How you will do it in a repeated fashion? The 0 you will give it here, right? And what is the remaining fractional part? You will write it here and you carry out this multiplication. Now the remaining fractional part is 0.625 and do the same operation here. Multiply by 2 again. And what is going to be the result? Can you tell me what is the result here? 0.625 into 2. It is, I mean, if it is difficult, the calculation, it is, let me tell you the answer, it is 1.25. It will be 1.25. In this 1.25, take this 1 to this side. We want to keep track of the integer part which you are getting in this multiplication, right? And leave the fractional part that is required for the next level of multiplication, right? So we want to keep track of these ones, these zeros and ones here, right? Then what you will do? What do you think will be the next multiplication? Can anybody tell me? I mean, this 0 is gone here, this 1 is gone here. What is the fractional part remaining in this one? What is the fractional part remaining in this one? It is 0.25. So the next level of multiplication will be 0.25 multiplied by what? 0.25 multiplied by 2. And that is equal to what? What is point? I mean, this is straightforward. 0.25 into 2 is equal to what? 0.5. Right? And in this one, take this 0. Take this integer part. Right? And write it here. Right? Now, what is the remaining fractional part? It is 0.5 multiplied by 2. And what are you going to get? It is 1.0. Right? And here the integer part is 1. And the next thing you need to understand is, what is the fractional part? The fractional part is 0. Now, once the fractional part is 0, you can end the process there. Once the fractional part becomes 0, you can actually stop the process, because what happens is that if you multiply it by 0 again, I mean, you're going to get 0 only. You're repeatedly going to get 0. So there is no point in continuing. So you have to stop here. Now, one more important thing, after doing all this, you have to read it from top to bottom. Earlier for integer part, you were reading it from bottom to top. For fractional part, this will be your, most significant bit, and this will be the least significant bit. And so basically, what will be the fractional part corresponding to this one? 0.3125. 0.3125, see, basically 0.3125 base 10 will be equal to what? I mean, it's a binary point. I mean, 0, 1, 0, 1. This will be the fractional conversion, right? So this will be the conversion to fractional part, right? So now how will you represent this overall thing now? I mean, you will write the integer part separately, separated by a binary point. You call it as a, see, in decimal system you call it as a decimal point. In binary system you call it as a binary point, the fractional point. So basically this particular number will be nothing but 100,101 point. And what is the representation of this one? 0.3125 is 0.0101. Sorry, 0.0101 base 2. So this is how you convert a mixed number. That is a number containing both fractional part, both in integer part and fractional part into any base system. I mean, this can be done for see. Let me do this one also. This is for converting from uh, what decimal to binary if there is a fractional part. Suppose you want to convert the same. Let's take the same number, 37.3125. Suppose this is 10. Convert this into octal. Suppose I want to convert this one into octal number system. So what should be the procedure first of all? I mean 37, the integer part can be obtained by what? A repeated division, right? 37. So 8. So this will be what? 8 fours are 32. And you have a remainder of 5. And this one will be 8, 0. This will be 4. So from top, bottom to top, and this will be equal to what? This will be equal to 45. So basically, this will be the integer part. I'm talking only about the integer part. The integer part will be 4, 5 base 8. What about the fractional part? Let us calculate the fractional part here. Say 0.3125, and you have to multiply this with which value? Which number? What do you think? 0.3125 has to be multiplied with which number? 8, 2, or which number? 8. It has to be multiplied with 8. And can you tell me what is the answer to this one? 0.3125 multiplied by 8. So you can calculate it. You can try multiplying this one. I think this will come out to be 2.5. Is it 2.5? Yes. So if it is 2.5, what you do is that you take the integer part here. See, whenever you're dealing with fractions, you take the not the remainder, you take the integer part of this multiplied result, right? So 2 is a candidate for our result. Then the remaining fraction, you take it downwards and you repeat this multiplication. And what is this one? 0.5 multiplied by 8. Can you tell me? What is 0.5 multiplied by 8? It is 4.0. Right? And what is the integer part of this one? The integer part of this one is 4. And you have already reached a 0. The fractional part is 0. So there is no point in continuing this procedure of multiplying. So once the fractional part is 0, you can stop here. And you have to read it from top to bottom. Right? And when you read it from top to bottom, this will be nothing but 0.24. It's an octal point. It's an octal point. Not a decimal point. It's an octal point. So 8. So altogether, now you can combine this with this, right? Integer part and decimal part. This is 45.24 base 8, right? I hope this part is clear. Is it clear, all of you? I mean, how to convert the integer part and fractional part into any base, any base. I mean, this can be done to hexadecimal also. This can be done to any base. If you want to convert it into base 7, multiply with base 7. If you want to convert it into base 5, multiply with base 5 or divide it by base 5. For integer part, divide it by base 5. For fractional part, multiply by 5. Right. So is this procedure clear? How to convert a decimal number to any base number system? Is this clear? Everyone? Okay. Chetana, that's okay. Clear. Okay. Good. Okay. So now we have covered how to convert a number from any base to decimal and decimal number system to any base. So these two things are done now. Now let us look at some more easy shortcut kind of conversions. Now what we have now looked at is decimal to any base and any base to decimal. Now let us look at some specific conversions, right? Specific specific conversions which are easy, which are very easy. Okay. So you don't have to divide or anything, nothing like that. So there are some conversions which are very easy. So let's see what are those conversions. So basically, suppose you have a octal number system. So basically, these conversions are octal to first one is octal to binary and binary to octal. Binary to octal. So you don't have to go through this boring division, multiplication. Those things are not required in these kind of these conversions are very simple to get. And in most of your exam questions, the questions given will be these kind of questions, which can be done in a matter of seconds actually. So binary to octal. Then the another one which is very easy is hexadecimal to, or it need not be octal and hexadecimal, it can be a power of any power of 2. But since octal and hexadecimal are the widely popularly used ones, we are only looking at these ones, right? Hexadecimal to binary, and similarly binary to hexadecimal. Okay. So let's see what is easy in this one. Say let me give you some number here. Say 43, right? And say point. Let me take a decimal. I mean octal point also. 0.5 52. So suppose this is in octal. I want to convert this one into binary. I want to convert this one into binary. What is one way of doing it? One way of doing is that, see, since it is in 8 and this is in 2, one way of doing it is that you can actually convert it into base 10. Then because base 10 is familiar to you, from base 10 you know how to convert it into binary, but that will be a very tedious process. That will be unwanted time wasting, right? Instead of that one, there is a very easy procedure. If this base is a power of 2, suppose this is base 2, and if this base is actually any power of 2, there is an easy method. It can be 16 or it can be 4. And if you want to convert binary to any of these bases, which are powers of 2, there's a very simple method. And what is the simple method? See, understand that. What are the let us look at the representations for 0. See, what are the symbols available in base? Symbols available in base available in base 8. Can you tell me this one? What are the symbols available in octal system? 0, 0, 1, 2, 3, 4, 5, 6, and 7. Right? One second, I'm sorry. 0, right? 0, 1, 2, 3, 4, 5, 6, 7. Now look at this one. This 0 can be represented as in binary as how many strings are required to see, how many bits are required to represent 0 to 7? See, 0 to 7 is 8 numbers. If you want to represent, yeah, you require 3 bits. Now 0 can be represented as what? So minimum bits I'm saying. 0 can be represented as a string of binary as what? 0, 0, 0, right? String of binary. String of binary. And 1 can be represented as what? 1 can be represented as 0, 0, 1. 2 can be represented as 0, 1, 0. 3 can be represented as 0, 1, 1. This should be in your mind, right? The representation for each of this digit. When it is 3, you should immediately understand the binary representation is 0, 1, 1. Right? Because this is required for our conversion. This is 1, 0, 0. 5 is 1, 0, 1. 6 is 1. What is 6? It is 1, 1, 0. and 7 is what? 7 is 1, 1 and 1, right? So you have to remember this string of binary representing each of the octal symbols. These are the octal symbols, right? And for each octal symbol can be represented by a 3-bit binary. So you need to remember this one. Once you remember this 3-bit binary, it is very easy to convert the octal number to binary. What you have to just do is that look at each symbol in this one. Look at the symbol 4, and can you recollect what is a binary string for 4? Can you recollect the binary symbol for binary string for 4 in binary? What is it? So this 4 is nothing but you can replace it by what? You just replace it by its equivalent binary string 100. That is 4 has an equivalent binary string 100. Replace it with 100. Now can you tell me what is the equivalent binary string of 3? What is the equivalent binary string of 3? It is 0, 1, 1. So put it here 0, 1, 1, right? Then put that point here. It is nothing but I mean the job here is very simple. Every symbol appearing in this particular number, replace it by its binary equivalent. Replace it by its 3-bit binary equivalent. You will get the binary representation of this particular number. This happens only if this base is a power of 2, right? So if it is 8, basically 2 cube is 8. So you will require a 3-bit string to represent what? 3-bit string to represent each symbol in your octal system. Now 5 is represented by what? 5 is represented by, so can you tell me this one? 1, 0. So please write it as 1, 0. So there is a point here. 5 will be represented by 1, 0, 1. And finally this 2 will be represented by what? 2 will be represented by 0, 1, 0, right? So that is the binary representation of this octal number, right? Now what happens if it is now similarly the same procedure can be let me write that. The same procedure can be applied. The same procedure can be applied for the conversion from what hexadecimal to binary also, because hexadecimal is also power of 2, right? It is 16. So 16 is also power of 2. So the conversion is very easy, hexadecimal to binary. But when you convert from hexadecimal to binary, can you tell me each symbol in hexadecimal has to be replaced with how many bits of binary string? It has to be replaced with 4 bits of binary string, because you require at least 4 bits to represent 16 symbols. Because in hexadecimal you have got 16 symbols, and for representing each of the 16 symbols you require distinct 4 bits. And so you need to remember what are the binary equivalent of those symbols, right? So this is quite easy. It's not very difficult to get the binary. See, one thing you can actually remember all. See, 0 is 0, 0, 0, 0, and 1 is 0, 0, 0, 1. So similarly, you can write all of this. You can remember. Or suddenly, if I ask you what is the binary of say C, how will you write that? What is the binary equivalent of C? 1100. And what is the easy way to write that one? What is the easy way to write the binary equivalent of a hexadecimal symbol? Suppose you want to write say something like maybe I can take D. And first of all, understand what is the value of D. What is the value of D? The value of D is, what is the value of D? The hexadecimal symbol D. What is the value of it? The value of D is 13, right? Is it 13? Right. Yeah. Now, how will you represent it as a binary? So what you can do is that, look at this one. You write the positional weight here. See, the first position is 8, second position is 4, third position is 2, 1. Now think about a combination, how you can get 8, how you can get 13 here. 13 is nothing but 8 plus 4 plus 1, right? 8 plus 4 plus 1 is actually 13. So whichever digits are participating in this one, put a 1 there. So it will be 1 here, it will be 1 here. 2 is not participating in this one, so 0. This will be 1. So it will be 1 1 0 1. 1 1 0 1 will be the the binary equivalent of this one, 8 D, right? So if it is 9, suppose I want to convert 9 to hexadecimal, to binary string. So how will I do that? And 9 is simply 8 plus 1, right? 9 is simply 8 plus 1. So what I do is that 1, 4 and 2 is 0, this 1. So this is basically 9. Right? I hope you understand. These are the positional weights, 8 4 2 1. Right? So just remember that. Standard binary weights are usually written like 8 4 2 1 coding also sometimes. Okay, so just remember this one. Now, how to convert? How is the conversion from hexadecimal to binary? Just as we have done in octal to binary. In octal to binary, what we have done is that each symbol is replaced by its 3-bit binary string. In hexadecimal to binary, each symbol in hexadecimal will be replaced by what? Each symbol in hexadecimal will be replaced by its binary equivalent. Binary equivalent of 4-bit binary string, right? So let me give you a number to convert to binary. Say, these are some of the very frequent examples used in this one. Classrooms. Bad dad, right? So this is a hexadecimal number. Now how will you convert this one to binary? Can you tell me what will be the binary representation of this one? What is the binary equivalent of B? Can you tell me what is the binary equivalent of B? See, first thing is, what is the binary equivalent of this symbol? What is the equivalent of binary equivalent of this symbol? It is 11, so it is 1 0 1 1. What is the binary equivalent of A? What is the binary equivalent of A? 1 before that. It is 1 0 1 0, right? And what is the binary equivalent of D? What is the binary equivalent of D? 1 1 0 1. Very good. 1 1 0 1, right? And that is done. That is the integer part. Now fractional part. This is D is what? 1 1 0 1. And A is what? A is nothing but 1 0 1 0. D is what? D is again 1 1 0 1. So this is your binary. You can obviously see that this conversion is much easier than decimal to binary or binary to decimal, these kind of things. Hexadecimal to binary and octal to binary, these are very simple conversions. Now, what about the reverse way? Binary to, see this, what we have done now is, if an octal number is given, we know how to convert it into binary. If a hexadecimal number is given, we know how to convert it into binary. And what you have to just do is that replace each octal symbol or hexadecimal symbol by its equivalent binary string, and write all, replace every symbol appearing in your number by its equivalent binary. You will get the corresponding binary of that particular number. Now, what happens if you are given a binary number and you are asked to convert? So conversion from binary to the other way around. Conversion from binary to the reverse direction. Binary to octal. How do you do this one? Conversion from binary. So let me give you one number here. Say 1010 0.0111, right? Suppose I give you a number like this. Now, what you have to do here is that this is a this is a number given in binary, and I want to convert this one into octal, a number in octal number system, right? Base 8 number system. Now, how do I do this one? Now, what I can do is that, see, in the reverse process, what we have done is that we have replaced every symbol by 3 bits. So here also, what you can do is that to the left of your fractional point, you group the bits from left to right by 3 bits. You group the bits from right to left by 3 bits. So this will be 3 bits. Now from here, do you have 3 bits here? Do you have 3 bits at this part? Here there is only 1 bit present, right? So how to make it 3 bits? How can you make it 3 bits without changing its value? See, if it is to the left of the decimal point, you can add any zeros to this part because it doesn't change the value of that number, because these zeros are insignificant. These zeros added here are insignificant zeros. So if there is only 1 bit left here, you want to make it 3 bits. How can you do that to 3 bits? You add 2 zeros here. Now it is a group of 3 bits. So you can group it into a group of 3. Right? And about the fractional part, what you do is that starting from the fractional part towards the right, starting from, see, for the integer part, starting from the fractional part towards the left, you group it by 3. And for the fractional part, starting from the binary point, you group it to the right by 3, group of 3. Right? So now this is a group of 3. And what about this number? This particular bit left here. It is only 1 bit. How can I make it into a group of 3? You can add as many zeros to the extreme right of numbers after the decimal point. These zeros doesn't have any value. These zeros doesn't change the value of your number, right? Now you have got a group of 3 here. Now each of this group has a symbol representation in your octal number system. Now you have to tell me what are each of these. What is 001 in octal? Yeah, what is 001 in octal? 001 in octal is 1, right? What is 010 in octal? What is 010 in octal? It is 2. And you have a point here. What is 011 in octal? It is 3. And what is 100 in octal? It is 4. So this is the base 8 representation. Right. Right. So I think that is clear. Now let us convert from hexadecimal binary to hexadecimal. It is almost similar. Instead of grouping as 3, you should be grouping as what? If you want to convert from binary to hexadecimal, instead of grouping the bits as 3, you should be grouping it as what? You should be grouping it as 4. So let us take the same number. It is 10.011.100. So this, this was something like this, right? So this was this the number given? This was the initial number given, right? Yeah, this was the number given, and we have padded some zeros to make it 3. So suppose this is the number, and you want to convert it into hexadecimal. So so let me take another number. Let me take another number. So let's take 110. So let me take 11010. 9.01. Okay. So let me take this one. And I want to convert it into hexadecimal, right? I want to convert this one into hexadecimal. Now, how do we do this one? Right. So first of all, please understand the same procedure from the fractional part to the integer part, to the left, You group it by not 3, you group it by 4. Yeah, very good. Answer is correct. I mean, you group it by 4. And here, when you try to group it by 4, you see only 2 bits. But 2 bits are not sufficient. So you will add 2 more zeros to make it a group of 4. So now this is a group of 4. Right? Now here you, from the fractional part to the right, you group it by, to the right, you group it by bits of 4. But here you find only 2 bits. So how to make it into 4 bits? You pad 2 zeros to the right of the rightmost one, right? So basically this will become what? This will become this one. Now replace each of this binary string by its corresponding hexadecimal symbol. So what is this particular symbol? Can you tell me? What is this hexadecimal symbol? 0011. What does that correspond to? 3. What about 1010? What does that correspond to? 1010 correspond to 8. Very good. 1010 correspond to A. Right? And what about 0100? What does that correspond to? It is 4. Very good. So basically now your hexadecimal number is 3A.4. Right? So is this clear, everyone? Is this point clear? Conversion from any number system to other number system. Is this clear? Decimal to binary, binary to decimal, and decimal to any base to decimal, right? Binary to hexadecimal, octal to binary, binary to octal. So yeah, these kind of questions are usually asked in exam, because this is easy and you should know the logic behind it. That's all, right? Most of the times they ask these kind of questions. So just remember this one. Okay. We'll discuss some of the problems, which is asked in competitive exams like BSNL and all other exams, UGC NET, BSNL, these kind of exams. Okay. Let's look at these kind of, these are the kind of questions which are usually asked in BSNL, JTO. They're simple. Actually, you can answer these questions. Now you have to tell me, if anybody knows the answer, you have to tell me the answer. Okay. Now, tell me this one. Digital electronics based on dash numbering system. So it should be obvious. Can somebody tell me the answer? Which is the answer? Binary. Everyone is right. I mean, all of you are giving the answers. I'm very pleased to hear that. I mean, everybody is getting the answer. Digital electronics is primarily based on which number system? It is based on binary number system. Right? It's a straightforward theoretical question. You can expect these kind of questions in your exams. Please remember, there will be a lot of theoretical questions. Okay, fine. Let's move on to the next question. Yeah, this one I haven't told you. Please understand. What is meant by a bit, byte, nibble, and word? Have you heard of this one? What is meant by bit, byte, nibble, and word? Yeah, I mean, you already got a bit is nothing but 1 bit, basically. It's 1 bit, right? And what about byte? It's a string of, it's a set of how many bits? Byte, you might be knowing this one.
8 bit.
8 bits, right? And what about nibble? Is it 4 bits? Yeah. And what about word finally? Word is usually 16 bits, right? Most of the times we refer word as 16 bits. There are occasions where word is not 16 bits. When you learn computer architecture and organization, sometimes they might give word as something else. I mean, word size can be something else, but usually the word, when you see word, it usually refers to 16 bits. Fine. So the answer, the answer here is what? The answer here is word. Okay. So just remember these points here. What is nibble? Nibble is 4 bits. Byte is 8 bits. I mean, those things. Okay. So these are theoretical questions. Now this one should be easy for you. Can you tell me the answer for this one? The base of the hexadecimal system is option B, right? Yeah, I think all of you are getting that one. Base of the hexadecimal, I mean, straightforward one. Base of the hexadecimal system is 16. Okay. Now, this one, the binary numbers value changes most drastically when the dash is changed. I mean, MSB, frequency, LSB. So let me give you just a simple example. See this one. See, suppose I have a 2-bit number. Yeah, very good. I mean, Pujari, it's very good. I mean, that is MSB. And why is it MS? Please understand, whenever I give you a number like 001, which is MSB here and which is LSB here. This is LSB, least significant bit. This is MSB, right? Now let us try changing this one. Let us try. So let's say this one. Let's say this is 010. What is this particular number? Can you tell me? This is 2. Now suppose let me change this LSB here. What will happen? 011. So I change the LSB. What happened to this number? This number will become what? What will be this number? If I change this 0 to 1, what will be the change in the number? The number will change to 3. The change in number is 2 to 3. What is the change actually? The change is actually 1. That is from 2 has changed to 3. Now instead of changing the LSB, suppose you change the MSB of this number, right? So change the MSB. Change MSB. What happens? This will become 1. Say this is 1, 0. Can you tell me what is this number? 110. What is 110? It is 6. And what is the change in this one? From 2, it has changed to 6. So which is more drastic? Which is a more drastic change? Change in MSB or change in LSB? What do you think? See, when you changed LSB, the change was only 1 unit. When you changed MSB, the change is 4 units. So which is a more drastic change? What do you think? What is the answer? So the more drastic change is obtained by changing MSB, right? Please remember, I mean, frequency and duty cycle has nothing to do with, I mean, the change in the number representation or nothing, right? Frequency and duty cycle comes when you deal with sequential circuits and when you deal with clocks, these kind of things, right? So, I mean, this is these options are not relevant here, actually. Fine. Okay. Now let's move on to the next question. I mean, this one, can you tell me the answer? Can suppose we have discussed a lot of things. Convert hexadecimal value 16 to so we have a number 16 which is in hexadecimal system. I want to convert it into decimal. So how will you convert it into decimal? So please understand what is the position of this one. This is 16 raised to 1 hexadecimal. This is 16 raised to 0. So what will be the number in this? But this will be the symbol 1. 1 multiplied by 16 raised to 1 positional weight plus 6 into 16 raised to 0. And what is this one? 1 into 16 is 16 plus 6 into 16 raised to 0. That is 16 plus what is 16 raised to 0? It is 1. So 16 plus 6 is equal to what? 22. So it is 22 base 10. Right? So are you all clear with this one? Is anybody having doubt? Is it clear, everyone? All of you. Is it clear? Okay. Yeah. Okay. So let's move on to the next question. Okay. Now convert the following, but it's not. Convert the following decimal number to 8-bit binary, and the number given is 187. 187. Convert the number to 187 to binary. I'll give you a shortcut trick here. I mean, if it is needed, maybe what you can do, you can divide it by 2. See, what you can do is that you can keep on dividing it by 2, and you can divide it like this. But instead of that one, I'll give you a short trick here. See this one. Let us convert it into hexadecimal first. That is, let us divide it by 16 first. Now, can you divide it by 16 and tell me what is the answer? What will be the hexadecimal representation? So 16 and 18 will be going by what? 16 and 18 will be going by 1. There is a remainder of 2. And in 27, what will be the what will be your 16 will go how many times?
1.
1 times. And what will be the remainder? 16 and 27. What will be the remainder? What is the remainder?
11.
11. And what is 11 in hexadecimal? B, right? Is it B? Is it A or B? It's B, right?
B. B. B.
Yeah. Now let's see this one. 16. This will go in what? 0, right? Then again, what is the remainder here? Is
B.
it B?
B.
Right. Now, basically, this is B in 16, but this is easy to convert to binary. And can you tell me what is the binary of B?
Hmm?
What is the binary of B? What is the binary representation of B?
1011 1011.
1011. What is the binary of B again? 1011, right? So what is the right option? What is the right? I mean, is it clear? Is this method clear? Is this method clear? I mean, what you can do is that you can divide by 2. There is nothing wrong in dividing it by 2. You can keep on dividing it by 2. I just try to make that division step a little bit simpler. That's all. By dividing it by 6.
Can we take another example, sir?
Yeah. I'll take another example. See this one. See.
DD, one more time, please tell me.
I'll take another example and just make it clear. See this one. Suppose I want to convert, say, 248 to hexadecimal. Say this is 248, right? To binary, right? I want to convert this one to binary. Now, what you can immediately do is that instead of keep on dividing it by 2, because it will take some time. I mean, you can divide it. It's not a very big task. You can do it in 2 minutes or 3 minutes. But instead of that one, why don't you divide it by? Why don't you just convert it into hexadecimal first? I mean, this division will not take much time. Now, tell me this one. 16 goes in 24 how many times?
1.
1. And what is the remainder here? The remainder here is 8. And what you have is 88. And in 88, 16 goes how many times?
1 day.
5 times, right?
5 times.
8, sir.
5 times. So what is the remainder here? 8. Correct? Is this clear? In 88, I mean 16 goes 5 times. That is 80. And what is the remainder? 8. Is that clear? Clear or no? Is it clear? Is this clear?
Yes.
Yes. Okay. Now, what you can do is that 16, this is 0, and this will be what? F. Right? So, what will be, let's first understand what is, this is F8, 16. Now, you can actually convert this into binary much, but what is F? F is nothing but 1, 1, 1, 1. And what is 8? Is it 1, 0?
1 triple 0.
1 triple 0? I mean, is there a 1, 0 something here? I'm sorry. Yeah, correct. Now 8 is nothing but 1, 0, 0, 0. So this will be the binary, right? So basically this will be 1, 1, 1, 1, 0, 0, 0. Yeah. I mean, you can actually divide it by 16. That will be much easier division. Division wise, it will be much easier. I mean, 2 will actually prolong the method. I mean, you have to carry out the division from top to end. Yeah, because once you get the 16, I mean hexadecimal, it's a natural. The conversion is straightforward, right? So it's easy to get the binary. Yeah. I mean, it will save your time many times when it is a very big number. If you're given some number like 2, 1, 5, 3, something like this, it is much better to divide it by 16 and then convert it to binary, right? Yeah. What about this one? Convert. So this, I think you should be able to do this one. convert the binary 1 1. So I don't know how many bits are here. 1 1 1 1. So 8, right? And then 0 0 1 0. So how will you? I mean, you have to convert this one into hexadecimal. So group it by 4. Right. So now tell me, what is this particular symbol? 2. What is this
F.
symbol? F. And this symbol is F. So what will be the hexadecimal? FF2. Right. So this will be the hexadecimal. So that is option B. Right. Okay. I think this is clear. So let's move to the next question. So what about convert the binary number 1001.0010? So it's a binary number. You have to convert it into decimal. So can you do that one? I mean, again, here also you don't have to multiply it by the entire. See, what is 1001? Can you tell me what is 1001?
9.
9. So you can directly write it as 9. There is no nothing like 1 into 2 raised to q. You don't have to write that. So the integer part is directly 9 point. What can you tell about this one? See, point. See, what is 0.00.0010? So there is only one. There is only one here. This is 2 raised to. This is 2 raised to minus 1. This is 2 raised to minus 2. This is 2 raised to minus 3. So basically what you get is 9 plus, and what is this number? It is 1 into 1 by 8, right? What is 2 raised to minus 3? 2 raised to minus 3 is 1 by 8, correct or not? Correct? So this is 1 by 8. And what is 1 by 8? Do you know what is 1 by 8? Is 0.125, right? 1 by 8 is 0.125. Now club this one with 9. So what is your answer? It is 9 point. So your answer will be B, right? So is it clear? Is this one clear? Is it clear?
Yes, ma'am.
Yeah. Okay. Now let's go to this one. Convert hexadecimal value C1 to binary. So there is a hexadecimal value C1. You have to convert that to binary. What is a binary? I mean, this should be easy for you. So C1 16 equal to, what is the symbol for C? Yeah, correct.
1100.
1 1.
A is the answer, sir. 1100.
Correct. 1100 and 1 is 0001, right? So basically this one is option A. Then convert this octal number to decimal. So there is an octal number given. You want to convert that one to decimal. So 17 octal, what is in decimal? So this is what you need to find out. So how will you convert this one? It's option D. Very good. It is 8 plus 7, that is 15, right? Okay, so the answer is 15. So next one. Convert the following binary number to octal number system, not hexadecimal, octal number system. So basically you have to group in 3 actually. So 0 0 1 1 0 1 0 1 1. So this is the number. You have to group from, it's an integer part, so you have to group from the left. Group of 3, group of 3, group of 3. So it's straightforward. I mean, this is 1, this is 5, this is 3. So it is 153 base 8, right? So 153 base 8, right? Okay. So that's also straightforward. Just you have to group it by 3. What about this one? You have a number. You have to convert this one to hexadecimal. So can you tell me the answer? I mean, it's a lengthy one, but you can actually do that. I mean, you can do it here itself. Let me write 1 1 0 0 1 0 1 0 0 0 1 1 0 1 0 1, right? So let us start grouping from left by 4. This one, right? Okay, now tell me which are these symbols. Now if I'm making something wrong, please notify. I may make some mistakes when I'm writing these things. Okay, so if I have done some mistake, please tell me. So this one is what is this symbol? The last one, 0 1 0 1. What is that symbol?
5.
5. This one is 3. This one, yeah, this symbol 1 0 1 0 in hexadecimal, A. This symbol 1 1 0 0, T. Right. So your answer should be CA35 base 16, right? And that should be your answer. So most of the questions are in this manner. Most of the competitive exam questions are in this fashion, right? So yeah, you can ask any doubts you are having. I'll be here to answer.
Yeah, see, sir, there's one doubt from Satyanarayana.
Yeah. Okay. Yeah, Satyanarayana, please. Yeah. Can you just ask? Do you have a chat? Have you posted it in chat, or you want to see?
It is there in chat.
17 base 8 to hexadecimal. Okay. Yeah. Okay. That's a good question. Okay. Yeah, Satyanarayan, let me just show you that. So there is a good question. I think I have missed out on that. This one, Satyanarayana, you are asking, you want to convert this one into hexadecimal, right? That is, suppose we want to convert this one to hexadecimal. What you have to do is that you actually bypass it through the binary. Don't go to the decimal part. You actually convert this one into binary first. What will be the binary of this one? Can you tell me the binary first? 17 base 8. I mean, you can use the conversion procedure for octal to binary. 1 will be represented by what? 1 will be represented by 0 0 1. 7 will be represented by what? 7 will be represented by 7 will be represented by 1 1 1. Now once you have done that, you have got the binary in place. Now you can easily convert this binary to hexadecimal. How can you convert this binary to hexadecimal? Yeah, this is correct, right? I mean, this is 1, and this one is 0 anyway. And what is this one? This one is equal to what? F, right? I mean, you have already got this one 15 here, so this will be F in 16, right? Because this is 0 and this is F. And if you get a bigger number, like something like say, I think it is clear, right? I mean, say, I tell you this one, 143 base 8, convert this into hexadecimal, right? Now what you do is that convert to binary first. How will you convert this one to binary? 1 is 0 0 1. See, this 1 is 0 0 1. And 4 is what? 4 is 1 0 0. And 3 is what? 3 is 0 1 1. Once you get the binary, you group in 4 now. Now you can convert this into hexadecimal. You can convert this into hexadecimal. So this one is 3. This one is what basically group of 0 1 1 0 is what basically 6, I think, right? And this is anyway 0, right? So this is basically 63 base 16, right? So is that clear, Satyanarayana? Is it clear?
Okay, if there is no more questions, we can wind up, sir.
It is a wonderful section, and Srijit sir has done a great work.
Yeah.
Very good class delivery, as well as the interaction was also good. Thank you so much, sir.
Yeah. Thank you, sir.